Hey there, I've got another practice physics GRE problem to work through tonight. It is number 44 off of the 1996 practice physics GRE. So I'm going to read the problem. It's a little fuzzy, sorry. Read along at home if you got it. Number 44. A particle of unit mass undergoes one-dimensional motion such that its velocity varies according to v of x equals beta times x to the negative n, where beta and n are constants and x is the position of the particle. What is the acceleration of the particle as a function of x? And then a quick glance at the answers before you start the problem. See what information can be gleaned from that. I don't see much. I mean, it hints that we're taking some kind of derivative, but don't let that, get you into a sense of security as to how to do the problem or whatever. You need to realize that you're going to have to pick the right one out of this. There's nothing you can really eliminate by, analyzing the units or anything like that. So we go right into the problem. The first thing I want to do is write that equation. V of x equals beta x to the negative n, because that's kind of the starting point. And now I feel a little worried about this problem, doing the narration of this problem, just because I'm afraid I'm not being very mathematically thorough about it, and I should be. I mean, I went through, I solved the problem, I checked the answer, it's the right answer. I just I don't want to be exposed for what a sloppy mathematician I can be some of the time. Always learning, you're always trying to tighten up your mathematics, obviously. But the way that I kind of solved this problem is right off the bat I looked at, it's a function of x, but I know also the velocity is going to have to be dx dt. That's the velocity equals beta x to the negative n. And so if I had to, I think at this point I could algebraically manipulate this equation around enough and solve to get this in a form that's better for me. You realize that as physicists we're not used to seeing this type of equation. We're not used to seeing a velocity expressed in terms of the x variable. In other words, if you imagine a basic kinematic problem like just dropping a ball under the influence of gravity, we don't typically write that as, okay, how fast is the ball going at 1 meter and 2 meters and 3 meters? We typically write that as how fast is the ball going at 1 second and 2 seconds and 3 seconds. But realize that this equation that they've given you is not what you're used to. It's not in terms of time, it's in terms of the velocity. And so, but still, you realize that that has to be equal to your time derivative of a function that is your position expressed in terms of time. And I'm sorry, I'm being vague, and maybe, feel free to correct me if you want to post a comment or a video response or something and just hotshot and showboat on your mathematics and say how I'm just, making a mistake here. By all means, go for it. But if you do it this way, you put dx dt equal to this. What you can do next, the way that I decided to try this problem, is to take a second time derivative of both sides of this equation, because I know that my acceleration, which is asked for in the problem, is equal to a second time derivative of the position function. Okay, so that's what I can get on this side if I take one more time derivative. So what I'm doing is taking a second time derivative, and now when I do that on this side, I have to take the derivative of this function. Okay, that's easy. This beta stays constant. I bring the negative n down as a factor, and I subtract 1 from that, so I get negative n minus 1. Now the key here, where you don't want to screw it up, is you're not done yet, because x is in fact dependent on t. You have to realize that x is in fact a function of t. I hope I'm saying that right and proceeding correctly with this problem, but x is a function of t, so you need to take the interior derivative of it. It's just basically the chain rule. And so I take one further derivative and I say I want to take that derivative, the time derivative of that function in there. And so this is my acceleration as asked for in the problem. Now the issue is, well, obviously in my answers I don't have a dx dt. I need to clear that out of there. Can I do it? Sure, because it's right up here. And so I can go back to here. So I just insert in here beta x to the negative n. And so I can put that together, and my expression comes out to, I have two betas there, so I get a beta squared. I have a negative n. You know what, let me write the negative n first, because I'm pretty sure that's how they would write it in the answer. Negative n, beta squared, and then I have x to the minus n minus 1 multiplied by x to the negative n. So we just add those exponents, and we get x to the negative 2n minus 1. And that's what I will be scrambling to look for an answer, and I hope I did that right. Is it there? It looks like it's there. I see it under answer A. Negative n beta squared x to the negative 2n plus, or sorry, x to the negative 2n minus 1. Okay, so that would be the one I would pick, answer A. And that is how I solved this one, number 44 on the 1996 exam. I would say that this is more of a calculus problem than a physics problem. I'd group it as a mechanics problem, but I would say it's more of a calculus problem. So, you know, I know you're out there, you're studying hard for the physics GRE to get into graduate school and do physics studies. You want to study physics, but remember, it doesn't hurt to go back and review your calculus too. Physics is just applied calculus. I mean, a lot of physics is just applied calculus, right? So I guess that's my little take-home bit for today. Is this is really a calculus problem described as a physics, disguised as a physics problem. So review your calculus, chain rule, that kind of stuff. Study hard. Good luck.